Hello, math fans. I'm Daniel Spielman. We're here in Heidelberg. I'm a professor at Yale in computer science, statistics and data science, and mathematics.
I'm very interested to hear that you described yourself as a professor of computer science, statistics and data science, and mathematics. Because my first question was literally going to be, would you describe yourself as a computer scientist or a mathematician?
I used to tell the computer scientists I'm a mathematician and tell the mathematicians I'm a computer scientist, so no one could get offended. Because then they don't own what I am claiming to be. But I really just never decided what I was going to be, and I live somewhere between the two. I like to do both.
I think that's really cool, actually, to literally, just kind of move between the disciplines in terms of what takes your fancy, in a way. No, I think that's really cool. Okay, and as you mentioned, we are here in Heidelberg at the Laureate Forum. Some of you, if you've watched any of my previous videos, may remember I've interviewed other laureates here in Heidelberg. This happens every year. It's an awesome event. It's the first time I've been here, and Daniel has also been here, so this is very exciting. And you are invited to this event if you've won one of what are, I guess, seen as the major awards within the fields of maths and computer science. The award that made you eligible for this, because you've won so many awards, was in 2010.
Yes.
And it was called the Nevanlinna?
Yes, they've renamed it now, the Abacus Prize.
Yes, and this is awarded by the International Mathematical Union.
Yes.
Okay, now I had a look online. You are only one of 11 winners.
That's right, once every 4 years.
Which is incredible. So I know this is never an easy question to answer, but as one of only 11 people to be recognized at that level, do you ever actually think about what that means, or would that just be too much to actually...
I think I usually don't think about what it means, and I think I was you have to be under 40 when you get it. Sometimes I think I was very lucky to the right birthday at the right time.
Were you close to 40 at the time? Or?
Yes, I was very close to 40. I think I snuck under by a few months.
Because obviously you could be like 37 or 41 as it fell, and then it's probably harder if you're because you've got fewer years to do your research.
Yeah. But it's given for people who are doing work in mathematical aspects of computer science, and that hasn't been a thing for that long.
That's
so
true.
The fact that there are 11 giving once every 4 years sounds pretty good. Yeah, pretty reasonable.
Yeah, no, it's awesome. Quick fire question number 1. What is the first piece of code you remember working on?
Oh my gosh. It was like a little adventure game on a Commodore PET. And I wish I still had the darn code. When I wrote it as a kid, I thought it was so cool. One day I found the tape that it was on, but that was long after my parents had gotten rid of the computer. So I have no idea what it was.
But in theory, if you still have the tape, could it now be...
If I could find the tape, in theory it could be run, but
Okay.
I don't know that I still
This is what YouTube exists for. I'm sure there is somebody watching this video who has the Commodore machine required. Right. Potentially. Let us know.
Now I'm wondering if I could find the tape, which is a really good question. Yeah.
Okay. As I mentioned, we are obviously here in Heidelberg. You've been doing some talks. We actually did a session yesterday where you had to do a 3-minute lightning talk.
Yes.
So I thought your talk was fantastic.
Thank
you. For the viewers, could you give us like a short summary of what the idea was? Because I thought it was a really nice way of describing what you do as a computer scientist / mathematician.
Yes. Well, I wanted to take the opportunity to give some advice to young scientists, and part of it was not just advice, part of it is what I'm always begging my students to learn to do. And what I find really useful when I'm doing math and trying to prove a theorem is I do computer experiments to try to find counterexamples and see if what I'm doing is true. And it has proved invaluable to me over my career. There's so many wrong things I have stopped trying to do because I found a computer counterexample. So I tried to motivate people to do this and to give them some encouragement for how to get started. And because that's the key part, like if you've never done it before, it's really hard. And when I tell this to students who haven't programmed much, they're just sort of terrified at the thought of beginning. And actually, even students who've programmed a fair amount, but just not done that sort of programming are terrified. But I always thought, like, why am I going to prove something that Gauss didn't? Well, I have a computer. I should be using this. And okay, it's not helping me find a proof, but it's helping me figure out which proofs are not going to work.
No, I like that because I think when I speak to research mathematicians, and particularly research mathematicians who work in more pure or theoretical fields, they say that they spend way more of their time trying to prove things that ultimately turn out to be incorrect than they do, trying to prove something which eventually they get. They're like, if it is provable, you will usually get it, unless it's Fermat's last theorem, you'll usually get it quite quickly. So that's just, it's just a really nice way to think about, as you say, the usefulness and the tool that we have now of computers. So why not use it to it's almost like, would you sort of think of it as like a first tick box? It's like, I think I can prove this particular thing, or I think this thing might be true. Let's just run it through the computer before I sort of spend lots of time actually trying to...
It's the first, second, and third. I run something through the computer, and sometimes I just find a counterexample immediately. The idea was just bad. Sometimes I don't. But then I'll say, okay, let's just let the computer run for a day or two. And sometimes, you're days in and it finds a counterexample. And if that doesn't happen, I'm like, okay, I'll email my co-authors. But with the caveat that it's been running on one core for, 2 or 3 days. Sometimes I'll write them back later, like, okay, it's now been a month running on 40 cores. We haven't found a counterexample. More likely true.
Okay.
But sometimes, it's been a month or two and I find a counterexample.
Yeah.
So, because some things just are sort of close to true, but not quite. But then when you learn what's not quite right, you change it. And often for me, it's not even what's true. Maybe my main goal is true. But then the question is, how do I get there? And the steps involved, I'm often working. So, I've been working for about 4 years on something. 1 year on this particular concrete approach.
Okay.
Where I've just been trying to figure out how to prove it. I have an algorithm. I think it works. I don't know. Each time I come up with a proof technique, I have managed to then figure out a computer experiment to test if that proof technique could work. And I keep breaking them. I think we have a proof technique now that we haven't broken yet. Maybe it's okay. But each time I learn something more about what not to do, eventually, hopefully, we just narrow it down and the only thing left is the right one. But I don't know how long it'll take to get there. I really don't.
And is this what you're talking about tomorrow, or is this because I am aware from my obviously researching your previous interviews and things, you talk a lot about working on several problems at once to sort of jump between them. So is this one of those cases where this is one thing and then the thing you're talking about?
The thing I'm talking about tomorrow, I guess you could say, is the paper I wrote, and what I'm working on is the paper I want to write to follow up.
Okay.
And the first draft of the paper I wrote was 4 years ago, which is why I've been trying to work on the next paper for 4 years. That's what I'll do tomorrow is, honestly, I'm going to spend more time talking about just some of the cool areas of math and computer science that go into this than my results.
Okay.
So there's this amazing area of work called discrepancy theory that is very much related to randomized controlled trials. Or I'd say randomized controlled trials, to use the old word, are the killer app for discrepancy theory. People were doing discrepancy theory long before anyone made the connection, but I will mainly just try to explain discrepancy theory, and I'll say a little bit about randomized controlled trials, and because I only have 20 minutes for the talk.
Yes.
And then people who want to know more can go watch a longer talk. I have many recorded, or read a paper or something.
Okay, brilliant. And when you say randomized controlled trials, so would that be in the context of a medical trial?
Yes. So the first ones we all think about, which makes it so easy today now that we had this COVID vaccine trials, right? You're trying to figure out, does this vaccine work? Yeah. But I got into this initially looking at public policy interventions. They're saying, here's this new educational policy or new curriculum. We want to try it out and see if it's better. They line up 100 schools. They try it in 50 of them or something. Yep. Or different public health interventions. So that's where I got started, because it was a colleague of mine in public health who told me he was setting up a public health intervention and he wasn't happy with the way the trial was looking. Right. And asked if I could help. So that's how I got into this. And the main difference between that case and testing a vaccine is, in that case, you've researched all of your experimental subjects very carefully before you start. Yep. When you're lining up schools to do a study in them, you know a lot about those schools. Whereas if you're doing something like a vaccine trial, people come into your office and you can't say, okay, come back 6 months from now and we'll decide whether or not we give you the placebo or the vaccines. You have to make decisions on the fly.
Yep.
And so anyway, that doing everything right when it's on the fly is what's been bugging me for 4 years now. And
Okay, and is there an easy to describe answer or a nice analogy about how you might go about that?
Okay, so why don't I say what discrepancy theory tells us? So the basic idea of discrepancy theory is if you give me a group of people, we can subdivide them into two groups so that the two groups look very similar to each other.
Yep.
Okay. Now, I should make that quantitative. I can't easily without a board, but if I were to say how similar, let's just say much more similar than if you were to do it at random.
Yep.
Okay, so that is the key result in discrepancy theory time after time. You can divide things up so they look more similar than random.
Yep.
And you think that makes a lot of sense if you're testing something out because you want the two groups you're testing it on to be similar.
Yes.
So that's why I thought discrepancy theory would be so useful for this. But it turns out that, yes, you do need randomization also. Otherwise, there's no statistics. And in the end of the day, we need to do some statistics and state things about p-values. So it's really about combining randomization and statistics with the way people have done discrepancy theory.
I see.
But everything I know, or my first paper on this, was geared towards the public policy case where we knew the subjects in advance. And what I can say now is I think we know how to do it when it's online and the subjects come in one at a time, basically just as well as if we knew them all in advance. But I don't have a proof that it's correct yet.
Right.
So until we have the proof, I don't. And here the proof matters. It's not just for the fun of it. Like you don't want to run an oncology trial and then have me say at the end, "Oops, the math was wrong." Right?
No,
like that would be inhumane.
Yes, no, definitely. Yeah. So this is hopefully as you say, you've been working on it for 4 years. Last year now
I think.
Fingers crossed. I'm sure we all have everything crossed for you.
Thank you. Yes.
Because I agree with you. It sounds like actually a really cool maths. I'd never heard of discrepancy theory, but it sounds awesome. I'm going to go and read about this. And as you say, like incredibly useful, like really, really valuable, which is always a huge bonus.
I mean, let me mention to you and anyone in the audience, like I'm sure people need to do this many times that I don't know about. Yeah. Like I was riding the train a year ago and someone asked me, just conversation, what I'm working on. And we started talking about that. And they're like, oh, that's funny. They're telling me they need to solve this problem. They're a teacher at the local high school. And when the new class of students comes in, they try to divide them up into different classrooms. Yep. And someone is spending a month over the summer with a spreadsheet of the students to try to make each classroom the same. Yeah. It's like, oh, well, we could give you code that would do that. That's discrepancy theory. And I'm sort of waiting to find out where else people need to do this.
Yeah.
Because it's sort of, it's like math. Okay, so first, mathematicians just proved it was possible. The first big result there was by Spencer in this paper called 6 Standard Deviations Suffice. That was like 85. We didn't actually have an algorithm for doing it quickly until 2010. Nikhil Bansal came up with one.
Okay.
So there was a good 25 years where it was like, we know mathematicians knew it was possible, but there was just no way if you really wanted to do it.
Yeah. If you want to learn more about discrepancy theory, you can access a free worksheet, which I've put together in Maple Learn, by clicking on the link in the video description. The interactive worksheet walks you through an example where we want to separate a collection of participants into two groups that look approximately similar, or as Daniel explained in the video, more similar than if they were random. In the first step, we assign values to each of the participants' characteristics, with 1 representing a positive answer and 0 a negative answer. We can then use the built-in floor and ceiling functions in Maple Learn to compute the average value for each variable. The values can easily be changed should you wish to do so using the interactive sliders. The participants are then randomly assigned to either Group A or Group B, and the sum of each variable calculated once again. This allows us to easily identify a characteristic which has not been equally represented across the two groups. I invite you to open the worksheet and to have a play with the data for yourself to see if you can find the optimal way to separate the participants according to discrepancy theory. And don't forget that if you want to access the full version of Maple Learn, you can sign up for a discounted subscription using the code in the box below. Something else that I came across when I was looking up sort of your work in previous interviews. You have a lot of notebooks.
Yes.
Do you know how many?
Oh, that's an interesting question. So if I think about, they're on average 3/4 of an inch, and they're taking up about 10 feet of shelf space in my office. So we're probably...
Like lengthwise 10 feet long.
Lengthwise,
Okay,
10 feet. Yeah, I use artist sketch pads.
Okay,
So then
yeah.
we're probably, oh my gosh, at around, what's that, 150? Somewhere between 120 and 150, I think. There are little gaps between the shelves.
And I noticed they were sort of sequentially, like month to year.
Yes.
So is each one like a 3-month period or something, or is it just however until it gets full?
Until it gets full. And some months are more productive than others. Usually I'm writing more during the summer. But I just write nonstop. It was, right, because otherwise you just, I describe it as you just sit there trying to think of things, and I don't know any better way to think than just start writing. And yes, most of it's junk, most of it's false, but at least I'm doing something if I keep writing. And then somehow, I mean, I put the date on the outside because I tend to remember when it was that I worked on something, so that I can go look it up. Right, so I keep them because sometimes I really do want to look up something that I did a long time ago.
Definitely, yeah. No, it was something that I wouldn't say my office mates made fun of me, but they commented during my PhD that I had a stack of like 45 like notebooks as well. So mine were definitely like the normal sort of lined A4 ring binder things, but I'd go through like one a month easily.
So I wish I'd done that in graduate school. In graduate school, I was just taking notepads, because I was cheap, I was a graduate student, writing on them and then stapling them at the end.
Right, okay.
And I still have those, but they don't hold up as well. And then I discovered artist notebooks, I mean, just a little bit more, but like $10, I can get a pretty good book, and that'll last 2 months at least.
Yeah, no, I think it's genius, literally. But I suppose, is there something about having the paper versus obviously you could do it electronically on a tablet now?
Oh,
or is it just habit? You had to start on paper and now you're just...
I do often do it on an iPad. Now I do both. It's going to sound silly, but like the iPad I can take with me anywhere. So now I've specialized. I keep the iPad with me everywhere, and when I want a notebook, I now got big ones. They're about 12 by 18. And that's actually really nice because then I can fit a lot on them. And yes, you say there is something about the paper. It is nice to be able to write out everything in color and see it all. But I guess that I'm using when I'm a little more organized, and then I'm just scribbling on my iPad nonstop. But I still keep it all.
Yeah. Awesome. No, as I say, I felt like I resonated when I saw it. I was like, I've definitely not got 150. Mine are thinner, but it did remind me of when I was a graduate student. Favorite number?
Pi.
Okay.
After that, E.
Well, I have pi and I have E.
Okay,
here,
but when someone says they're guessing a thing for number between 1 and 10, that's just never it.
Yeah.
It's very disappointing.
Okay, so a few other things that I came across that you'd spoken about, which I felt might be quite helpful for mathematicians watching, sort of young researchers. That's, of course, a big theme of Heidelberg.
Yes.
Is you are all here as the laureates to meet all the young researchers, PhD students, postdocs. And you talked, I think, about two things that I found really interesting that I think I would have really appreciated as a graduate student. One of them was this idea about your sort of constantly thinking about very hard problems. Sort of, I think I found some sort of quote that you said, something about you want to work on like the hardest stuff because everything is hard when you try and do it. So why not go for the really, really, that everyone else says is also really hard, which I think is awesome. But I guess, how do you even begin to attack a problem like that?
Oh, that's a good question. I mean, so Right. If I want to think about a hard problem, I have to have a belief that I have some leverage.
Okay.
If I can't come up with any insight or any leverage, I'm not going to start.
Okay.
But I'm willing to wait. I mean, I have lists of problems that I would like to work on. And every once in a while, if I don't have anything to do, I can look at them and go take a walk and see if I can come up with an idea.
Okay.
And I'll admit, right, there's only like really a few problems that I find I can't think of anywhere to start. I mean, my ideas might be bad, but you have to deceive yourself into thinking that they're good and going with it. Otherwise, you never get anywhere.
Yeah.
I mean, sometimes I work on something and I've got an idea and I'm very excited about it. And then after a couple weeks, I finally understand the idea and I realize, oh, this has all been done before, that approach. But then at least I'm angry enough that I'm willing to push forwards and come up with another idea.
Okay.
Yeah, it's only things like P versus NP, which is one of the hardest problems in theoretical computer science, I've never had a reasonable idea about. I've never been able to make myself think for more than 10 minutes. I had a reasonable idea about it. It's a very frustrating problem.
That's why it has the $1 million prize.
Yeah,
right?
$1 million doesn't
Everything
begin to get there if you solve that one.
I once saw actually, it's of course only one of the million
Yes.
problems. The Poincare conjecture is the one that was solved. I saw an estimate of the amount of time that was spent working on that. And when you worked it out, your hourly wage would be less than minimum wage.
Yes, I tell my students there are easier ways to get $1 million. Right?
It's probably the hardest way to get $1 million, right? But
right, raking leaves, shoveling snow, that would be better. Yes.
Yeah. Something else that struck me reading more about your work was, and I don't know whether this came from you or came from the person that interviewed you, but they sort of framed it about saying you were able to like make the most of failures and use that to kind of motivate you or to use that to learn from and things. So I suppose, I think that's something that every mathematician, computer scientist faces. You're not going to solve every problem that you try to think about. So again, what is your advice, or let's say like top tip or tips around, you get to a point and then it doesn't work and you're obviously quite deflated. Like, you know, do you have a personal thing you do in that moment or?
Yes, I really do. I mean, honestly, most of my papers have come about from not solving the problem I set out to solve.
Okay.
I just think if you work on something hard enough, you eventually have some idea. And if it doesn't solve what you want to solve, I then try to figure out, well, what does that idea let me solve?
Yeah.
Because often what you're doing is the goal is just to have an idea or come up with a new technique or something. But this does take knowing your field well enough to figure out what those possibilities are. So this is easier for computer scientists, because in computer science, it's easier at an earlier stage in your career to get an idea for what other people will find interesting and what's the breadth of it. In mathematics, it's harder. Usually, like young mathematicians are just trusting their advisor to help them.
Yeah.
And hopefully, when you go to your advisor and you say, I didn't solve the problem, but here's what I did, your advisor will say, oh, that might be good for something else. Now let's go look at that. But yeah, so many things I did, and well, probably most, really just came about because I tried something and it didn't work for a problem. Then I figured out what it would be useful for. I learned something. Yeah. I mean, I admit my grad students sometimes I think find this frustrating. I give them a problem. I don't think they can solve it. I'm just hoping they'll come back and tell me something interesting. What did they think about? Yeah. And then we'll figure out what that's good for.
No, I think that's an amazing, I think failure is the wrong word because the way you've just described it is, it's just you have done something and therefore you have learned something from that.
Right.
So that is, I don't know, failure is just such a negative,
that's
such
true.
Negative associations to it.
But, I mean, you need a way to prompt yourself to come up with a new idea.
Yeah.
Right. I mean, I think it's like worth looking at how artists do that. Like often they'll give themselves what you may think of as artificial constraints on how they're going to design something or depict something or write something. I mean, I think about like most poetry is to some degree putting an artificial constraint on how you're going to use language, but then it winds up producing something beautiful. Like so you need to think about these sorts of things, try them out.
Yeah, I love that. Solving a math problem is literally poetry.
Yes.
Okay, and then the last thing that I enjoyed, sort of, again, looking through your past interviews, you mentioned, I think it was actually an interview at the HLF, about a piece of advice you had for young researchers, which was to say, sort of figure out what your limited number of talents are, because and then maximize those talents that you have. And I think that's a really logical and like almost like a mathematician's way of thinking about things, which I love as obviously someone who clearly thinks like a mathematician. But I was intrigued as to what might you describe your specific talents that you have maximized.
An interesting thought, right? And I should add, I do try to learn other talents. I try to learn how some people do other things. It's hard. I mean, okay, for me, like the first one of those is like, I just think about like, can I imitate my professors? Like when I was a student, that would help me put myself in their mindset. But the things I do particularly was one, think about one thing for a really long time. And I mean, I know that, right? Like I can sit and think for 4 hours, 8 hours, whatever. I'll be happy doing that. Wow. Doing computer experiments is a big advantage, and I leverage that a lot. I mean, part of it is because I'm also a computer scientist, and but also I've been doing it forever. So there's a lot of things which, right, like I know I can come up with a computer experiment to test that a lot of people would have a much harder time with it. That is some advantage. I have somehow developed some weird intuition for eigenvalues and eigenvectors. Okay. And from, I guess, looking at them a long time. And I know I can use that. I can take derivatives really well. Computing Lagrange duals, not as much. I try to get a friend when I need to do some things. Right, figure out some of these superpowers. I know that I can explain and convey what I'm doing really well. Okay, so I mean, that's one reason, but also and I'm pretty good at picking out what other people will find interesting. And this is actually like a really useful thing, especially in more mathematical disciplines, because there's a lot of theorems you could prove, but it's worth proving what other people will find interesting. And you know, it's always obvious that some big named open problem will be interesting, but you got to come up with others.
I think, again, probably sound like a broken record. Like, I think that's just a really nice way of thinking about your own like ability and strengths, and like as you say, actually it feels like it's really worth taking the time for anyone out there who is in the student stage of your career, or even any point in your career. I think it is actually incredibly important to realize, what am I good at, what are my strengths, and how can I actually make sure I'm using those.
Right. I mean, I've developed a few I didn't have. Like when I was in undergraduate, well, okay, I know I certainly had a very hard time doing any sort of symbol manipulation. I'd copy, you know, one line to the next, trying to simplify something, I would make a mistake. It was a nightmare. I did get over that. Like, I'm better at that now. Okay, and I'm pretty happy about that. Still, I will go to symbolic math package just to check my work. Because, you know, when it gets pages and pages, it's worth checking. So I have a truly awful memory. I have never recovered from, like, that has never improved.
The notebooks, you don't...
I keep, exactly. So a lot of what I'm doing is compensating for what I don't do well. Right, I have an awful memory. So yeah, like I also just wouldn't work in a field where if I had to memorize too much and have it right at the ready. I can keep things in my head short term very well. Like whatever problem I'm working on, sure, I'll keep that in my head. I can keep things, but long term, no. But yes, I have a lot of notebooks. I index them so that I can find these things later.
And last one, tabs or spaces?
Spaces.
Okay. I think spaces is winning so far. This has been asked to all of the sort of computer science people I've spoken with, and there seems to be a very strong preference for spaces. So, okay. Any reason? Any elaborate on?
I can always type 4 spaces and it sort of looks like a tab.
Yeah. All right.
But it's just what I do. It's habit.
Perfect. Well, thank you so much. This has been great fun. I've had a good time. Hopefully, Daniel's also had a good time.
Yes.
Hopefully, a lot of you watching have had a good time. And if you have, please do remember, like, subscribe, the usual YouTube drill. You know what to do at this point. And I'll be back soon with more maths. Take care.